Right. So, welcome to you all, and in this particular lecture we are going to discuss the formulation of integer programming problem. In our previous lecture we have discussed different types of integer programming problems, and we have seen what are their pros and cons, what are certain difficulties, and how they actually put before us certain formulation challenges, right. So, in this lecture we take up some of them and try to see how do we formulate such problems. So, let us take to begin with the first, we discussed these type of problems like project selection problems, facility location problems, assignment problems, traveling salesman problem, fixed charge problem, cutting stock problem, set covering problems, and so on. So, let us take the project selection problem, which is like a knapsack problem. So, there are 5 projects, as we discussed in the previous class, that there are 5 projects, the costs are given and the return after 3 years are also given, and if our purse, that is the budget, is 18,000 rupees, which projects will be chosen so that the net return after 3 years will be maximized. A project can be chosen only once, right. So, what should be our decision variable for such a problem? We have discussed in our previous lecture. So, you know by this time the decision variable has to be that whether a given project is chosen or not. Is it okay? So, that means xi or xj equal to 0 or 1, xj 0 means given project j is not chosen, xj equal to 1 given project j is chosen. So, having said that, these are our decision variables, and our formulation should therefore be the maximize the return. So, you see what are our various values, that is 9,000, 11,000, 6,500, 15,000 and 14,000, those are our returns. So, maximize the return from these projects subject to the initial cost, that is these values 5,000 x 1, 6,000 x 2, 3,500 x 3 less than equal to 18,000, where x j is between 0 and 1 for all I 1 2 dot dot 5, right. So, that is very simple. We formulate this problem, that is the project selection problem, and this formulation is very similar to the knapsack problem, is it not. So, if you recall what used to happen in knapsack problem, that maximize the value and subject to the individual items, and x 1, x 2, x 3, x 4, x 5 are their numbers and within the total weight limit. So, this is our project selection formulation. But the additional question that we also raised at that time, that at most 3 projects can be selected. So, how do you formulate this? So, you see there is x 1, x 2, x 3, x 4, x 5. These are our 5 decision variables. Now, if x 1 equal to 0, that means project 1 not selected, and obviously x 1 equal to 1 means project 1 selected. So, if you say at most 3 projects can be selected, how do you put that? if I add all the 5 xi's, then what should I get? You see, not more than 3 of them should be 1, is it not? That is the maximum. It cannot be 4 or 5. Is it okay? That means the sum over I equal to 1 to 5 xi should be less than equal to 3, right. So, at most 3 projects can be selected, and if project 2 is selected, then project 1 must be selected. How do you do this? What does it mean? It means that if x2 equal to 0, then that means project 2 is not selected, then x1 could be 0 or 1, is it not? But if x2 equal to 1, then x1 should be what? It should be 1. That means, you can easily understand that if x2 equal to 0, then x1 could be 0 or 1, but if x1 equal to 1, then x2 equal to 1, then x1 should be equal to 1. That means, you can see this, x2 should be less than equal to 1. That is the solution to the second problem. This is the solution to the first problem. And if project 2 is selected, then project 4 cannot be selected. That means, if x2 equal to 0, then x4 could be 0 or 1, that is fine. But if x2 equal to 1, then x4 should be 0. Is it all right? So, what can you comment about x2 plus x4? x2 plus x4, its maximum value should be 1. Why? Because let us write it down, number 3, x2 plus x4 would be less than equal to 1. What does it mean? That if x2 is selected, let us say x2 equal to 1, then x4 should be 0, right, because if x4 is also 1, then x2 plus x4 will be 2, right. In that case, it will violate the constraint. But if x2 equal to 0, x4 could be 0 or 1, right. So, there is no difficulty there. So, this is how we actually can take care of such constraints. So, let us see how this, here it is written that x1 plus x2 plus x3 plus x4 plus x5 should be less than equal to 3, and x2 is less than equal to x1, and x2 plus x4 is less than equal to 1, right. So, this is how all these additional constraints could be really done. So, there could be many such questions you can raise, that if you select 3, then you cannot select 1 or 2. Out of 1, 2 and 3, only 1 can be selected. So, like this you can think of various if then else conditions which can be actually modeled with the 0 1 variables very nicely, right. Assume that if in a different problem where I have these xi is not 0 or 1, xi's are actually integer numbers. So, if xi's are integer numbers, then these additional constraints cannot be done in this manner. So, in that case you have to define another set of binary variables, is it not? So, if those binary variables will be such that if a given project is selected, then the binary variable is 1. It does not matter whether 1 or 2. If it is 0, then those variables are 0, but if the variables are more than 0, then this binary variable will be 1. and then these relationships are to be then put in terms of those binary numbers, right. So, having said that, let us look at the fixed charge problem. So, how do you go about this? How do you go about putting the fixed cost variable? See, look here, I explained it in the last lecture that if you really take the total cost, let us say TC, if you take total cost TC equal to FCI plus VCI star Xi, right. So, Xi is whether a given type of project clothing type, shirt or shorts or pants are taken or not. So, if you take this way, the problem is when Xi equal to 0, then TCI equal to FCI and not 0. So, this is the problem, that when Xi equal to 0, then TCI equal to FCI and not 0, but what we really require is that TCI should be equal to 0. So, what is done? We take another variable y, yi, right, and we make the model in a different way, that is we make TCI equal to FCI star yi plus VCI star Xi. So, moment you take it, you have to ensure that when Xi equal to 0, then yi is also equal to 0. You have to ensure that. Is it all right? Now, question is, how do you do that? So, precisely that is what is modeled, and let us see how this is modeled. You see what you can do, the rest of the things are easy to model, that without rent consideration you can simply take the 12 x 1 plus 8 x 2 plus 5 x 3 which are like profit, and 6 x 1, 4 x 2 and 8 x 3 they are like cost. So, the profit minus cost, and then the 12 x 1 8 x 2 that is like the revenue minus cost, that is the profit, and that will be maximized, and subject to the labor constraint or the clothing constraint, that is the 3 x 1 plus 2 x 2 plus 6 x 3 less than equal to 150, and 4 x 1 plus 3 x 2 plus 4 x 3 less than equal to 160. They are like the usual linear programming formulation, and x 1, x 2, x 3 they should be greater than equal to 0 and they should be integers, right. The question is, how do we consider the fixed charge? So, here we do what we really do is that we take a large positive number mj and we put an constant, that is xj should be less than equal to mj yj. What does it mean? Where the yj is a 0 1 variable, is a binary variable. So, why does it work? Please think over. What really happens is that when you have added these additional variables 200 y 1, 150 y 2 and 100 y 3. Now, what are these 200, 150 and 100? These are the rents, right. So, these 200, 150 and 100 these are rents. So, what you do? You are taking that rent also. So, profit will go down by that amount, and in other words these two terms, this is the fixed cost, this is the variable cost, this is the revenue. So, revenue minus variable cost minus fixed cost. The idea that is xj should be less than equal to myj. See, the point is that we are maximizing a function. So, when we are maximizing a function, tell me what really happens is, let's understand this carefully. Supposing x j is less than equal to m y j or m j y j, or where m j is a large number. Let us say if x j equal to 1, let us say x j equal to 1, an integer number other than 0. So, if x j equal to 1, what will be the possible value of y j? Think over. If y j equal to 0, see y j is a binary variable related to the rent. If y j equal to 0, then what will happen? It will become 1 less than equal to m multiplied by 0. Is it possible? It is not possible. 0 cannot be greater than equal to 1. So, if x j equal to 1, then y j will also be 1. So, you see this particular relationship, that x j less than equal to m j y j will ensure that at any time if x j equal to 1, that means that a particular activity is there, it is produced, that means the clothing machine is used and we produce some clothing, let us say shirt or whatever, then y j should be 1, that there will be a rent, the rent component will be definitely there. But what happens if x j equal to 0? That means the activity is not there. Then from the type of equation you can see y j will be 0 or 1. We do not know, because both will be valid. It will be y j can be 0, that is also going to satisfy, y j equal to 1, that is also going to be satisfied. So, how do you take that particular thing out here? You see, the interesting thing is that we have an objective function which is maximizing. So, this is a maximizing function. Now, in this function, tell me if y 1 or y 1 is 0, what will be the functional value, and if y 1 equal to 1, which will be the functional value? Can you see that objective function will be higher if y j equal to 0? You see, if x j equal to 0, that this activity is not there, then it is a maximization problem. Now, if y 1 equal to 0, then this term will be 0. That means, the maximization will be whatever quantity we get from other consideration, this term will not be there. But if y 1 equal to 1, then this 200 y 1 will be 200. So, the objective function value will be reduced by 200, which is not a very good idea, because the objective function goes down. So, objective function will be higher if y j equal to 0, and since it is a maximization problem, that is what will be selected. So, if x j equal to 0, then by the nature of the problem y j will be 0 also. So, we get what we desire, that if x j equal to 0, then y j will be 0, and if x j equal to 1, then y j will be 1, and that is what we want, right. We want the rent to vanish if there is no activity, that is x j equal to 0, and we want rent to be there if the activity x j value is other than 0. That means, if activity is there, rent will be there, is all right, and if activity is not there, rent also will not be there. So, both are accomplished, one by the condition that we have taken and the other by the nature of the objective function. Is it all right? So, that is how we model what is known as the fixed charge problem. So, let us see how do we model our next one, that is the cutting stock problem. So, the cutting stock problem, which a picture has been depicted from Gilmore and Gomory's paper, which is one of the very fundamental work on such cutting stock problem. But whatever, we have understood that there is a continuous sheet and customers demands various width. So, how should it be cut into strips to meet demand while minimizing either amount of raw material cut or amount wasted. So, that is the example we had taken, that customers demand 25 3 feet boards, 25 feet boards, 15 9 feet boards, and company has got different 17 feet boards. So, the idea is how do I minimize the waste. So, what I discussed in previous lecture, that we can think of different cutting patterns, right. Like what I said, that from a 17 feet board, from a 17 feet board. So, if this is my 17 feet board, a given cutting pattern. So, cutting pattern 1 is 5 into 3 feet, right, cut 5 3 feet, but then it leads to 2 feet loss. Then there was cutting pattern 2, that was what we said, that 9 plus 5 plus 3. If you do that, then 0 trim loss, there is no trim loss. Think of another cutting pattern, cutting pattern 3. How about 3 5 feet, right? Again we have 2 feet trim loss. Like this, you can think of different cutting patterns, and when you cut in those different cutting patterns, you can have different kind of patterns. So, this is how they may look. So, here is some different at least 6 cutting patterns that has been thought about. So, supposing you can have 5 3 feet sheet cut, in that case the waste is 2, because 17 feet wide 5 3 feet sheet will take 15 feet, waste is 2. Let us say how many of these cutting patterns we use, let us say x1. Another pattern could be 4 3 feet 1 5 feet, then there is no waste. Then 2 3 feet 2 5 feet, that also is possible, in that case waste is 1. Then 2 3 feet and 1 9 feet, again waste is 2, 1 1 1 waste is 0, 0 3 0 waste is 2. Is it all right? It is not given because it is very much loss making, that is could be 1 9 feet, no, it is not possible, then you do not waste 8 feet, that is okay. So, these are the 6 patterns in which we can cut the 17 feet wide board into different cutting sheets as per customer demand. So, you can see the what will be the objective function. The objective function will be minimize waste, total width of boards cut minus total demand. So, 17 into x1, x2, x3, x4, x5, x6. So, you see total width of boards cut. So, x1 number, look here, x1 number of pattern 1, x2 number of pattern 2, x3 number of pattern 3. So, into each is 17 feet, and these many products are to be finally obtained, because we do not want any more customer demand, only this much customer demand. So, total customer demand is 310. So, that is the minimizing, but this is a constant amount. So, as an objective function this much is sufficient. In other words, this is sufficient, right, because that is only a multiplication. So, if I take these as my objective function, that should be okay to make this formulation. Now, the idea is that look here, in the first pattern I get 5 3 feet, second 4, third 2, fourth 2, fifth 1, 6 0. So, 5 4 2 2 and 1, that should be 25, that much should be available. Is it all right? The next one, x 2 plus 2 x 2 plus x 5 plus 3 x 6, that should be more than 20, that is for the 5 feet, and x 4 and x 5 should be 15 because 9 is only on x 4 and x 5. So, that should be there, and each x I should be greater than equal to 0 for all I as integer. So, that is how you can actually formulate the cutting stock problem, right. So, you understood how do I formulate these cutting stock problems, but the question is they are all integers. Now, the set covering problem, already I have discussed what is that set covering problem. So, let us say a government wish to locate several medical emergency response units, so that it can respond to calls within the city with 8 minutes of the call. Now, the city is divided into 7 population zones. The time travel between the centers of each pair of zones is known and is given in the matrix below. Look here, it is not symmetric. So, you see, if I locate my team at zone 1, then what will happen? Look at zone 1, this is our zone 1. Can you tell from zone 1, if I look, if I put my medical emergency team facility, then it can serve to which locations? It can serve to location 1, location 2, location 4 and location 7. It cannot serve location 3, location 5 and location 6. Why? Because those distances are higher than 8. All right. Can you now tell, if I locate in location 2, what are these locations or in zones where service could be given? It could be in 1, in 2, in 5, in 6 and 7, right. So, that is how we can start looking into it. The essential idea is where to locate these emergency response units, so that all the zones could be covered within 8 minutes. That is the idea. So, it is a kind of facility location problem, but it should cover the entire set. That is the essential idea, right. So, if that is so, now let us look at what really happens further, that x j equal to 1 if medical emergency response unit is located at zone j and zone j and 0 otherwise. So, look here, that is how the set covering problem can be formulated. The minimize 100 x 1 plus 80 x 2. Now, what are these 180 and all that? You see, the 180 and all that is the response units can be located with a cost of 180, 120 etc. So, these are the cost. So, we have to minimize the total cost. So, if I locate x 1 number in the first, so that will be the total cost will be this, that should be minimized, and our idea is x 1 plus x 2 plus x 4 plus x 7 should be greater than equal to 1. Is it okay? And x 1 plus x 2 plus x 5 plus x 6 plus x 7 should be greater than equal to 1 to cover zone 2. Is it all right? Similarly, in all of these, now why it should be x 1, x 2 and x 4 and x 7? Look here, what we found in the first zone, it can cover 1, 2, 4 and 7. So, that is why 1, 2, 4 and 7. Is it all right? So, that means that if each zone must be covered at least by one medical emergency response unit. So, we have x 1, x 2, x 4 plus x 7 that should be with 1 to cover zone 1, and similarly for all of them when we put and we get the solution will give that what should be our overall coverage, and obviously each one is 0 or 1 binary, because that is how we go ahead with it. So, with this what we do that we have seen how we model different kinds of at least 4 types of different problems, how do we formulate, right. In our next lecture we will continue these formulations, and we shall see how do we formulate other kind of problems like either or constraints or k out of p problems, the 0 1 problems, the binary problems or mixed integer problems, and go ahead from there to how to solve integer programming problems, right. So, thank you very much for this lecture.